You're listening to Let's Talk Creation, the science podcast that's just for you.
Well, hey everybody. Hope all our listeners and viewers are doing well. We're here for another great episode of our podcast, Let's Talk Creation, with Paul Garner and Todd Wood. I am Paul Garner.
And I am Todd Wood.
As always, remember to click the subscribe button, like and share our episodes, leave us a positive review, all of those things. We really appreciate all of that. And Todd, we've got a very interesting episode here for people.
Yeah, this is going to be really interesting. You're right.
we hope that it's going to be the beginning of a kind of an occasional series. Is that right?
Yeah, this is a complicated topic. We've been talking about doing this for a while, and people have been asking about it. And it's just one of those things that is not easy to understand. And so, we're going to sort of introduce things today, and then we're going to need some help from some friends to help us sort through some of the complexities.
Okay. Now we're being a little bit mysterious here.
We're a little coy with this. What are we talking about?
So the topic is dating methods. We're going to be looking at geological dating, and in fact, maybe other types of dating as well. So that's basically the topic. We want to kind of introduce things here and begin to sort of lay some foundations for perhaps delving into more of the technical details in other podcasts. So that's what we're going to talk about. We're going to talk about dating. And I thought in order to kind of kick this off, I wanted to show you, Todd, this rock specimen.
Okay. That is a rock.
So that is a rock. It's very difficult probably for you to see, but it's actually a fairly rusty red brown kind of color.
Okay.
I'm not sure whether that comes across on the video, but that's the color that it is. It's got some fairly jagged edges. It's quite sharp.
Oh.
It's got some shiny crystals in it, I think. And, it's got lots of holes in it. It's just riddled with holes. So it's actually not quite as heavy as perhaps you think it might be. And the question I wanted to ask you is, how old is this rock?
So one thing I can tell you is, I assume, since you have this rock in your house at the ready for this episode, it must be older than 5 or 10 minutes, right? Because you've at least brought it in from the outside, whatever it is.
Okay.
So it's got to be at least that old.
Yeah. So it's been sitting here on the table waiting for us to kind of start this podcast. So it's a few minutes old at least.
Yeah.
And I'm going to give you another clue as well.
Okay,
so I'm going to tell you. I'm going to tell you what kind of rock it is.
Okay.
It's a piece of volcanic rock.
Okay. Oh.
Okay.
All right. Well, now that helps as well. So I don't. Well, now see, this is tricky because I know there are volcanic rocks in the UK.
Mm-hmm.
But if it's from an actual volcano, then it's going to be from somewhere else. Now, I'm not familiar with the kinds of rocks around your house, but I'm going to guess that it's not from your local neighborhood. You had to go somewhere to get it, or somebody had to go somewhere. So there's a history there as well, right? So there's some kind of time that it took you to go and collect this rock where it was sitting on the ground.
That's absolutely right. And I'll tell you where I collected it.
Oh, great.
I actually collected it in Germany.
Okay.
In Bavaria.
Okay.
And I collected it in September 2019.
Okay. Oh, so it's recent. Recently collected.
Yeah.
Okay. So it's a Bavarian rock. Now, there's no active volcanoes in Germany that I am aware of. So I'm guessing it's not from a recent eruption. Because I'm assuming, I think people have seen the news broadcasts coming out of the Canary Islands with that horrible slow eruption of lava that's been eating up people's houses and so forth. Yeah, I'm assuming that's where the rock originally came from. So something like that, right? So there was a volcano that made some lava. Am I on the right track?
Yeah.
Yeah.
So
it's a volcanic rock in that sense.
So it's a volcanic rock, and this particular kind of volcanic rock is called scoria. Now,
scoria.
Scoria is actually a Greek word, and it means rusty. And that makes sense because this rock has a reddish color to it.
Yeah.
That might also be a clue.
Yeah, because by training, I'm a biochemist. But I know a lot about chemistry, so I know that reddish color to many volcanic rocks is the result of rust, essentially. I mean, there's iron that's contained in those rocks, and when they're produced, they're black, right? So people have seen the news, and they have seen that these freshly produced volcanic rocks are black. They're really shiny black. Mm-hmm. And over time then, and this may surprise some people, but over time, they don't stay black, and they don't turn gray. They actually kind of turn red. And the older it gets, the redder it gets, because all that iron is effectively rusting. Is that correct? Do I have my story right there?
Yeah, that's absolutely right. Okay. So this, again, we're beginning to uncover the history of this rock, aren't we? So we know it came from a volcano.
Yep.
We think it wasn't a recent volcano because there aren't any active volcanoes in the region where it came from. It's rusted, so it's been exposed to the atmosphere, and there's been some oxidation.
Yep.
It started off black. I guess one other thing, another clue about the age of this rock is that I'm holding it.
Ah, yes. It's not hot, right?
It's not hot.
Yeah. So that's actually one of the quicker things that happens, right? So when the lava comes to the surface and flows out, and now it's cooling, and then it's cool enough to touch, but it can still be black when it's cold enough to touch. So the fact that you're holding it also gives us that little clue that it must have been long enough for it to cool down so that you could hold it. All right. Yeah,
that's right. So this was probably the crust of a lava flow, that's cooled down, and then it's been exposed to the air, and so it's gone rusty. So we can get some clues, can't we, that this rock has a history, even if it's just the history that we can deduce from those fairly basic clues. So we know it's got to be older than a couple of years or so, because that's when I collected it.
Sure.
And it's got to be even older than that, because clearly it had a history before I collected it.
Sure.
So this kind of gets us into the topic of today. How do we know how old things are?
Yeah.
Geologists obviously have lots of methods that they use to try to decipher the history of objects like this volcanic rock. And these methods often yield results, apparently, in ages of hundreds of thousands, millions, even billions of years.
All right.
And of course, those kind of dates, those ages that geologists come up with, take us way beyond anything that seems consistent with what we read in the Bible, right? So what do we do about this, Todd? How do we, as creationists, we're confronted with these dates that geologists come up with. What do we do about this?
Yeah, it's sort of the fundamental. In my mind, it is one of the most fundamental questions that a young age creationist sort of has to contend with. And that's just what appears to be this evidence that these rocks are so much older than the thousands of years that we discern from the Bible. And so to a great extent, I think a lot of what we believe about creation kind of hinges on this question. What do we do with these radiometric dates? And so I just used a big word, radiometric dates. You've been calling it geological dating. You've obviously got more experience talking about it with the public. I just go right to radiometric dating. So we've reasoned through all these things, and we've said it must be, at least 2 years or 3 years old because you've collected it 3 years ago, and it must be older than that because it came from a place where there's no volcanoes going on now, and we figured it's older because it's sort of reddish and it's not, it's rusted, it's experienced this chemical weathering. But geologists they just want more detail, right? They want to know, okay, well, how old exactly is it? So there are these methods, this collection of methods, and I think they're complicated. And this is one of the reasons why we've decided we want to go pretty slow and have a lot of episodes. So I don't think we're going to answer any of our big questions today. But, and I really mean that. So I don't want people to come away thinking, oh, they didn't say anything at all. I want you to understand this is the beginning of a journey, and I hope you'll stay with us to continue along the journey. But the basic idea, as I understand it as a biologist and a biochemist and not a geologist, but there are elements, and I'm talking periodic table of the elements. Think back to your chemistry class in high school, wherever you've had, your chemistry understanding, and there are these things called the elements, and they are the most fundamental units of chemistry that we have. And sometimes you find these elements that are unstable. They produce radioactivity, right? And so this is the basis of your nuclear reactor that produces power. I know that's pretty common there in the UK. It's a little less common here in the US, but I've got 2 nuclear reactors pretty close to my house. Wow. I could drive there within an hour, and I could come to 2 different reactors. So that kind of thing. You have these elements that produce this radiation, and as they produce the radiation, the element changes into another element altogether. And it turns out that process is we believe that it's very regular, that it happens with a certain regularity. And so if you're able to make accurate measurements, you should be able to figure out how long ago that radioactive stuff started to decay. And
sure.
I'm sure people are already lost. Maybe we can go back. Let's think back here a second about that rock that we were just looking at, right? So we mentioned 2 things that could help you understand how old the rock was, that might help you understand what we're talking about with the radioactivity. One thing we said was the heat, right? So when that lava flows, it's incredibly hot, thousands of degrees, and then over time it cools. And everybody's pretty much been experienced with this kind of thing. You know that if you have a hot pan on the stove, you got to let it cool before you touch it with your bare hands. You know, on a hot day, for example, you know that your car seat might be really hot to sit on. You might want to put a towel on it. And you might want to turn that air conditioner on a hot day to cool your house, and that's going to take some time. So there's a process of cooling. And if you could tell us that cooling happens at a certain rate, then if you could take the temperature of a thing, you should be able to reason back to, well, it must have been cooling this long if it started out at molten rock temperatures. and I think to a lesser extent, you could do that with the rusting issue. Although rusting is a lot more irregular. It's not very reliable in terms of how fast things rust. So I don't think you could look at something and say, oh, this is really rusty. It must be 532 years old, because rusting depends on water. Rusting is not exactly like other forms of weathering, and so it depends a lot on water. And so if there's a lot of water, it happens quickly, and if there's not as much water, it happens more slowly. So it's not as reliable. But geologists tend to think that this radioactive decay of elements that are found in rocks is pretty regular and can tell us how old the rocks are. Now, Paul, when I say there's radioactivity in a rock, is it dangerous to go outside? Do you have to have lead gloves and shielding to hold your volcanic rock there?
No, you don't. Some people have had problems, of course, if they build their homes on granite and they get radiation build up in their homes.
Wow!
From the granites that they've built their homes on. But generally, no. It's not dangerous to handle the rocks themselves. Now, I was interested in what you said there, because really you're kind of putting your finger on the nub of the whole issue here, which is that if we want to try to estimate the age of something, you're really looking at a process, and you're looking at a rate of change. And you're then trying to extrapolate that backwards in time to work out when did that process begin. That's in effect what you're doing, isn't it?
That's exactly.
And so that's what you're doing with, how long it takes something to cool down, how long it takes something to rust, how long it takes for certain isotopes to build up in a rock.
Yeah.
Whatever it is, it's kind of the rate of change, and then you extrapolate that back in time.
Yep.
So that's a really important principle, and we're going to come back to that. And I think what we kind of want to do in this series, and it's going to be an occasional series. We're not going to just sort of do consecutive episodes. We're just going to keep coming back to it every now and then. But we want to try and help people understand, where do these dates come from? What are the uncertainties? What can we know, and what are the kind of unknowns, and how can we as creationists sort of interpret these dates within a different kind of framework? And hopefully we're going to consult with some other experts, maybe have some interviews and so on. But one of the things I find as I think we're already finding it as we start to talk about radiometric dating and radioisotopes and radiation, these things get technical really
fast,
quickly.
Yes.
and one of the things that we don't want to do is just to lose people, or to just sort of bamboozle people with the technical details and the jargon. We want to try and help people to really understand this, but it's not an easy job, is it, to actually try to unpack this in a way that's understandable to most people.
No, you and I have both given talks to various Christian groups, churches and schools and so forth. And I know there's a point. I can see it in their eyes when I've gotten too technical, and I've lost them, and they have no idea. And now they're just sort of sitting there daydreaming about when I'm going to stop talking. And and it's a shame, because this to me is a very important issue in the world of creationism. And there's a lot. There's so much to the nuance and the details that gives us, I think, hope for understanding what all of this means. Not just showing that the dates are wrong. That's interesting, I suppose, but that's really not what I'm after. I'm after, what is all this? There's a distribution of elements in these volcanic rocks that is relatively reproducible. And so what does this mean? What does this tell us about the actual history of the world? Not just the millions of years, but yeah. And so, I think it's not just a matter of going slow. We need to bring in experts, and we need to make sure that everything that we say is very clear. Because I don't want this to just be episodes for really smart people who can figure out what we're talking about. I want it to be for everybody, so that they can all have a basic understanding of these kinds of questions.
Yeah, and it is a real challenge, because as you try to simplify things, the danger is that you actually skip over some of the really important details, and that those who perhaps do have a bit more knowledge about some of these subjects feel that you're not dealing with the issue adequately. So, it's a very fine line for us to kind of tread between trying to get to grips with the details, but also to keep it understandable. And it's not going to be easy. I remember, I've given loads of talks over the years to all kinds of groups, from children and young people to adults, popular audiences, as well as sort of scholarly meetings. And so I have quite a lot of experience, I suppose, in trying to communicate some of these issues to people. But I remember giving a talk once about sedimentary rocks, and I thought I'd kept things pretty simple, and I think trying to explain sedimentary rocks is nowhere near as difficult as trying to explain radiometric dating. But I remember afterwards a lady came up to me and she said, look, you talked about sedimentary rocks being laid down. What does that mean?
Yeah.
And I suddenly realized that my best efforts to communicate had completely failed. That people often, we use language, we use jargon, and people really haven't kind of grasped what we're talking about. So, and that's the limitations partly of us as communicators. But to be frank, this particular topic of dating, the concepts are just quite difficult. So it's we're just going to have to work really hard to try and communicate it well.
It's sort of this intersection of physics. Nuclear physics and geology, and I understand things about it, but I can't say that I really understand everything that goes into this and how it all works. So I think it's really important. So I thought maybe we could just talk about give something of an example that maybe people could find a little more accessible. And the example I thought of that might help people think about this is the idea of a drippy faucet, right?
Yeah.
I think we've all been in a house somewhere, I know I have, where the faucet's starting to go bad, or the gaskets or whatever in the pipes that keeps the water from flowing out when you turn the knob off. And you have a drippy faucet, and it's dripping. And so a couple years ago, I had a drippy faucet, and I decided I didn't want to waste this water. I didn't want to just let it run down the drain. Which is weird because I live in an extremely rainy part of the country where water will literally fall out of the sky pretty much every week. So it's not like we're, in any danger of losing water. So, but anyway, I thought I would catch this water. So I put a jug under the faucet and catch the water. And it was empty, and I went to bed, and I got up the next day, and this jug was full. Absolutely full of water. So this drip was not just a a minor thing. It was producing at least a gallon of water overnight. And so you could figure that out, right? You could say, all right, there's a gallon of water. I put this jug under there and I've got a gallon of water now, or whatever, 4 liters of water. If you're not using the American system anymore, like literally the rest of the world. But anyway, so I've got this jug of water, and I could sort of, do some math, and I could say, well, I put it under the faucet at 10 o'clock, and I got up at 6 o'clock, and it was full of water, and so produced a gallon of water in the course of 8 hours, and so then I could figure out how fast it's dripping. Right?
Sure.
Because you would take the amount of water you have, divide it by the time, and boom, that'll give you the rate. You could also, I suppose, if you had the ability, you could measure an individual drip. And it's a little trickier because I think most people do not have the equipment to measure a volume that's quite that small. But you could use a stopwatch to figure out how fast the drips come and how much is in a drip, and then figure out the rate at which your faucet is leaking.
Sure.
Now with radiometric dating, so that's all basic stuff. We can understand that. It's pretty simple. So
I should interject here and just and just translate not only your measurements, from imperial to metric, but also faucet. So a faucet in Britain is a tap.
Oh no! I did not know that. Okay.
Just in case anybody is a little bit unsure what a faucet is.
A leaky tap.
It's a tap.
All right.
I'm sure most people know that.
Okay, I hope so.
I'm being facetious, really.
No, but that's good. That's another Britishism I did not realize was different between us. Okay.
Yeah.
I did not know about the tap. Okay. Well, there you go.
Yeah.
So leaky tap. That's what we're talking about.
Leaky tap. Yeah.
All right. So what the radiometric dating comes down to. So what we talked about here is basic figuring out speed, right? You have a distance or some amount of stuff that's happened, and you divide it by the time it took to happen, and you get your average rate, your average speed. Okay, so if I gave you a cup of water, and I said, Paul, my faucet is leaking 1 millimeter every 10 seconds, and I gave you a cup of water that had 500 milliliters in it, could you tell me how long my faucet, that cup has been sitting under that faucet? Is that possible?
Well, sure. I mean, you like you say, you can just divide the the amount in the cup by the rate at which the faucet is leaking, the tap is leaking.
Okay.
And you could work it out, and you could come up with a number.
Okay.
But
is that reliable though? Do you think that's a reliable estimate?
Well, this is what I was going to come on to, because the problem is that we're making some assumptions here, right? Now they might be reasonable assumptions. Yeah. And they may be assumptions that we could even test, and we could work out, are we making reasonable assumptions or not?
That's right.
But we are making some assumptions. So what are the assumptions that we're making? I think there are probably at least 3 main assumptions. One is concerning the initial conditions, right? So I guess one of the questions I'd want to ask is, are we sure that there was no water in the cup to begin with?
Right. When I put that cup under the faucet, was it dry? Did I just literally pull it off pull it out of the cupboard and put it under the tap, and it was empty and dry, and the water that was accumulated because of the dripping?
Yeah, okay. Because that's not immediately obvious.
Right. No, it's not obvious because it's all water, right? So if I put it under there half full, and with 250 mils, and then It dripped another 250 milliliters in. The time that it's been under the faucet changes.
Yeah, sure.
Right.
And another assumption that we're making is about the history of the system. So I'm assuming that while my back was turned, somebody else didn't come in and just put more water in the cup, or even take some water out of the cup.
Yep.
I'm also, I think, making the assumption that the cup itself is not leaking water.
Yeah.
Is there a crack? Is there a crack in the cup?
Yeah.
So that's another assumption. Again, without a little bit more consideration, those things are not immediately obvious. And then the third assumption that we've made is that the rate at which we've measured the leak, the rate at which the faucet is leaking, has not changed.
Right.
I can measure the rate it's leaking now, but how do I know it wasn't leaking slower or faster when I wasn't looking, earlier on?
Yeah.
Because that's gonna affect the calculation that I make.
Sure. Yeah, and leaks tend to get worse over time too. So
right.
So it's possible that over the course of however long that cup was sitting under there, that the leak has gotten worse, and it's now leaking faster than it was when it started. So, and all of those things will change. If the leak starts to leak faster, then there will be more water accumulated. And if we think that it leaked slower, then we're going to think it's been under there a lot longer than it has.
Sure.
If when I gave you the cup of water to tell me how long it's been under there, if I took a swig before I gave it to you, then I removed some of the evidence of the history, right? Or if the cup has a leak, it's lost some of that evidence of history as well. So you do have to make assumptions about the system in order to be able to say, well, I guess it's been under there this long. You've been listening to Todd and Paul Talk Creation. If you'd like more information on sponsorship opportunities, or maybe you'd like to have a product or book reviewed or discussed on our podcast, please contact us at podcast@coresci.org. That's podcast@coresci.org.
Do you have questions regarding the Young Age Creationism model? Well, we've got you covered with a book by podcast's own Paul Garner. His book, The New Creationism, was dubbed the single best book on creation and the flood by filmmakers of Is Genesis history. If you don't already have a copy, be sure to check it out on Amazon today. Now, let's get back to the podcast.
And I think what's important to point out to people is that all of the assumptions that we've just been talking about are not unique to the example of the leaky tap, the leaky faucet. So the same kinds of principles can be applied to radiometric dating, or indeed probably to lots of other systems that we might think about that could give us an age, some estimate of age.
Yeah.
So we could think about all kinds of processes, the travel time of starlight. We could think about the erosion of rocks, as well as the decay of radioisotopes. And, in all of these examples, we're making certain assumptions in order to then be able to deduce an age from those processes.
Right. And I think where the part of the reason this gets complicated is because we're dealing here in the U.S. in math education. You would call it maths, I believe, maths education. We have the dreaded story problem, right?
Right.
That's what this is. This is a grand and glorious story problem. It is like the old. If a train leaves London at noon and it travels so fast, this fast, when will it arrive in York? And I hope people are laughing, thinking, well, that depends on how fast, how often it stops and whether there's a problem and delays and who knows what. Yeah, that's exactly the problem, right? That's what we're talking about. You have to sort of make an assumption in order to get the answer to your story problem. You got to make some assumptions about
Yeah.
Is the train going to be delayed for some reason, or all those sorts of questions.
And it's always dangerous to make assumptions about the British rail system, because it could be leaves on the line, it could be the wrong kind of snow, it could be a replacement bus service because of engineering works. So you're probably going to be wrong in estimating what time it's going to reach York. So.
Right. So yeah, but that really is. That's the core of the problem of this issue of radiometric dating, and I think it's part of why people have a difficult time with it, because you end up with this. It's a story problem, and nobody liked story problems when they were in school. You just would rather have the numbers sort of laid out and just do the math and then get an answer, and having to figure out the story problem is challenging. But yeah, the British rail, there you go. Brit Rail has got all these these challenges and delays, and so yeah, you have to make certain assumptions. So, but you mentioned, when we were talking about the faucet, you mentioned that it's possible that you could test some of the assumptions, right? So you mentioned one of the things that you mentioned was, is the cup leaky? You could test that, right? If you you could take the cup and you could empty it of all water and then put some water in it and put some pressure on it and see if the water goes squirting out somewhere in a crack or something. So you could test that assumption. And that's something that comes into play with geological dating as well. It's not that geologists just make a bunch of wild guesses and wild assumptions that they can't ever know. There are ways of testing some of the assumptions in order to figure out if you're making some reasonable assumptions in order to solve the problem.
Sure. Yeah, so I think what we're beginning to understand is that actually this whole issue of dating things is actually quite complex.
Yeah.
And it's not straightforward. One of the things I often point out to people when we think about the radiometric dating of rocks, there is no clever machine in a laboratory somewhere where you can put a rock sample into the machine and it gives you a date.
Right.
That isn't how this works.
No.
Right. What happens is you send a sample off to a laboratory and they analyze the sample and they can tell you the ratio of certain radioactive and non-radioactive isotopes in the rock. And then on the basis of the kinds of assumptions that you make about the initial conditions and the nature of the system through time and the constancy or otherwise of the process rates, then you can interpret that isotopic analysis as a date.
Yeah.
But that's what a radiometric date is. It's an interpretation of an isotopic analysis of a rock.
Yeah.
So interpretation always, goes into these things.
Right.
And that process of interpretation is not simple and straightforward in many cases. And so, like you say, geologists are well aware, aren't they, of the various problems, the challenges involved in dating specimens and making sure those specimens are not contaminated in some way, or whatever it is, and they've developed over a long period of time different processes and techniques for trying to correct for those things, or to calibrate for those things, or making sure that you select your samples very carefully. That scientists are careful. They try to minimize all of these sources of bias or other problems, but nevertheless we're dealing with the real world, and the real world is complex.
Yep.
and it's difficult.
Yeah.
And sometimes, you talked about the assumptions. We can test some of the assumptions. We can test whether the cup has a crack in it, and is the cup leaking. But there might be other assumptions that are actually much harder to test.
Yes.
They're just simply harder to check.
Yeah.
And and we have to deal with those kinds of unknowns as well.
Yeah. Yeah, I remember, and it's not just, you talk about the complexity. I remember I don't know, it must have been 20 years ago. I visited the Institute for Creation Research back when they were still in California. Mm-hmm. And Steve Austin took me through the geology lab there. And he showed me a little vial of, looked like dust to me. And he told me he had processed this rock sample and gotten out these crystals that he was going to have dated. So your little piece of scoria there, right? That's not even what the geologists are going for when they're, well, at least in some cases, that's not what they're going for. They're going to process that rock and find particular parts of it that they can then date. So
sure,
it gets really complicated. It's not as easy as me handing you a cup of water and saying, how long has this been under my leaky tap?
Right.
There's just a lot to it.
So you can date in a laboratory. You can estimate the date of whole rock samples. You can take individual mineral components from the rock and date those individually. You can even, believe it or not, actually take individual crystals and date particular parts of the crystal. Wow. So you can do it at that kind of micro level.
One crystal, not just a vial full of crystals, but one crystal.
Yeah. You might have evidence of growth, layering within the crystal where the crystal has grown and accreted.
Oh yeah. And
you may well be able to, date different parts of that crystal.
That's amazing. That is really amazing that we've gotten that amount of, let's call it technical prowess, technical finesse to be able to look at individual parts of a single crystal. That's really astonishing. So let's get back to radiometric dating here and the idea of these radioactive elements that give off radiation and turn into other elements. So the radioactive element itself, we usually refer to that as a parent, right? Colloquially, maybe you'd call it a parent element.
Yeah. So just to kind of go back and sort of review some of the things you said earlier, radiometric dating, and actually it's a whole set of methods. It's not a single method because there are lots of different methods that are all called radiometric dating.
Yes.
So radiometric dating uses these naturally occurring radioactive elements to try to estimate the age of rocks and minerals. And to kind of understand how they work, we talked a little bit about the elements. Think about the structure of an element. So you have a nucleus of an atom. The nucleus of the atom contains positively charged particles called protons and particles that have no electrical charge called neutrons. And then orbiting around the nucleus at various distances are negatively charged particles called electrons.
Right.
And chemical elements are basically classified by the composition of their nucleus, by the number of protons. That's called the atomic number. And then if you add up the number of protons and neutrons, that's the atomic mass, right? Mm-hmm. And you can have forms of an element that have the same number of protons but a different number of neutrons, and we call those isotopes.
Yeah.
You can kind of think of them as species of the same element.
Sure.
Right?
Yeah, and I think that's really weird for people to understand that it is chemically the same thing.
Yeah.
But physically it's slightly different. And I still don't have a good analogy for it. I don't have a good analogy for how this works. But one example, so hydrogen is the simplest element. And it is a component of water. You know that. So H2O, that's water, and the H stands for hydrogen. And a hydrogen, the typical the most common hydrogen nucleus has a single proton in it. It's just a proton. But you can also, there's another version of that, an isotope of hydrogen that can have a proton and a neutron. And that actually doubles the mass of the hydrogen. Yeah. So you can have water. You can actually do this. This is pretty cool. You can order this online. You can order something called heavy water. And it is water that chemically acts just like water, but it is using the heavier isotope of hydrogen. So the same volume of water from your tap will be lighter than the volume of heavy water.
Yeah.
Which is super weird.
Yeah.
I mean, that's just a really mind-blowing idea. And if there's a place that we're going to lose people, that's one of the places. This idea that you can have exactly the same stuff. It will act like, chemically, it will act exactly the same. You would not know chemically that there was any difference there. But physically, it would be heavier or lighter, I guess, if you have a lighter isotope. Yeah. But that's kind of what isotopes are all about. You have those variants of the same exact thing.
That's exactly what they are. They're kind of species or varieties of the same element.
Yep.
And the important thing for radiometric dating is that many of those isotopes are unstable.
Yes.
Okay, so they're unstable, and what that means is that they spontaneously decay over time by emitting electromagnetic radiation and charged particles.
Yep.
And we don't need to get into the details, but there are different types of radioactive decay. But
that's a little. We don't need that. But
we'll
the basic idea there.
So they decay.
The isotope is most isotopes are going to be, well, not most. A lot of isotopes are stable. So heavy water is stable. That double, that neutron with the hydrogen nucleus with the neutron and the proton, that's stable. But if you add another neutron to it, so that it's now got two neutrons and one proton, that's called tritium, and that's radioactive. That's unstable.
Yeah.
So it breaks down.
Yeah, and they decay spontaneously. So, like you said a few moments ago, the unstable radioactive isotope we call the parent. And it decays over time, often through intermediate steps, until you reach a stable, non-radioactive product that we call the daughter.
Right.
So you have a parent that decays into the daughter. And at this point, I suppose we need to introduce another concept that, again, is probably going to be quite difficult for a lot of people, but it's the concept of half-life.
Right. Because this is not, it's not a linear decay, right? It doesn't happen at the same rate all the time. It's actually a bit faster when you start, because what we find with this radioactive decay, if I give you a certain amount of stuff, and it literally... that's radioactive, and it literally doesn't matter how much stuff I give you, but the amount of time it takes for half of that stuff to break down into a stable daughter element is always going to be the same. And it's weird. It has to do with the statistical properties and the probabilities of decay and quantum mechanics and stuff I don't even want to start getting into because I probably don't even understand it. But the basic concept is important, that it doesn't really matter how much stuff you start with. It always takes the same amount of time for half of that stuff to go away.
Yeah. And
so we always measure the inferred age of things according to how many half-lives we think it's been.
Yeah.
It's been going
That's
on.
exactly right.
Yeah.
So the half-life, like you say, it's the time taken for half of any given amount of the parent to decay into daughter. So imagine you start with 200 atoms of a radioactive parent isotope, after one half-life, half of those atoms will have decayed into daughter atoms. So you'd be left with 100 parent atoms.
Yep.
But then after another half-life...
The exact same amount of time.
Exact the same amount of time.
Right.
Half of the 100 atoms that you were left with would then have decayed into daughter.
Yes.
So you'd now be left with
Now you
50.
have 50.
50. And then after another half-life, which is again exactly the same amount of time, half of the 50% that you had left would now have decayed. So you'd now have 25 atoms
now I have
left.
25. Yeah.
And so this is how it goes on.
Yeah.
This is the concept of half-life, and it is quite difficult.
It's really weird, right?
For people to understand.
If you think, I've got 200 atoms, and in 100 years, I've got 100 atoms left, you would think, oh, well, then in another 100 years, I won't have any. They will have all decayed away. But that's exactly wrong. Yeah. That's not how it works. In fact, in another 100 years, you'll only have 50 atoms, which...
Yeah.
What is it? It's a very strange process. So...
Yeah. And for those who are technically minded, we call this exponential decay.
Yeah.
Right? This is exponential decay.
Yep.
It's described on a graph by an exponential curve. But it's a strange concept. But that's how it works. That's how the decay process works. And that decay process that we've just been talking about is then what's used as a kind of clock to estimate the age of rocks and minerals that contain these radioactive parent isotopes and their daughter products. So just to kind of, bring this back down to earth a bit. So take my my volcanic rock here. Okay. Imagine, this rock was erupted as lava from a volcano. As it begins to cool down, it begins to harden and crystallize. Okay, so crystals begin to form. And those crystals will incorporate into them those radioactive isotopes. Okay, parent isotopes. And those parent isotopes will decay into the daughter products, into the daughter isotopes.
Right.
And when that rock cools below a certain threshold temperature, it will begin to accumulate daughter atoms at the expense of the parent atoms which are decaying.
Okay, so you're saying that there's a point in that rock's history from being molten to being a solid actual piece of rock. There's a point there at which it's no longer accumulating the parent, right? And it now begins to just accumulate the daughter. Is that right?
Or losing the daughter.
Right. So it's no longer accepting any more parents, and it's not losing any daughters. Yeah. It's kind of crystallized, right? So
it's crystallized, and in fact, I mean, even that is a gross oversimplification because, individual minerals in the rock might have different temperatures at which that happens.
That's right.
So it's actually very, very, very complex.
And you also have the chemistry of it all because these are atoms, right? Mm-hmm. So there are some crystals that just don't like to have certain atoms in them. And sometimes there's a phase associated with it, right? So one of the radioactive elements that decays, there's a radioactive potassium, which is a metal and a solid, and it decays and becomes argon, which is a gas. And so there's all sorts of tricky stuff. Like you say, it's not as easy as just crystallizing and then that's it. There's no more parent added and there's no more daughter lost.
Yeah.
You got to be careful. So anyway, but go on. Yeah.
So theoretically then, given what we've just said, we should be able to use the simple accumulation of daughter products in a particular rock or mineral sample to estimate the age at which that, the age of the rock, the time at which that rock formed.
Exactly.
if we know three things, right?
Yep.
And those who are perhaps ahead of the curve might remember what we said earlier when we were talking about our leaky faucet, our leaky tap. There are three things we need to know, right? So, Todd, remind us what those three things are.
We need to know what we started with. Mm-hmm. We need to know that we haven't lost or gained any of that daughter element or parent element across time.
Yeah, except through radioactive decay.
That the changes in the amount of parent and daughter have only been due to the radioactive decay. Just like we said with the cup. The amount of water in the cup is only due to the dripping faucet. It's not due to anything else.
Yeah.
And then we have to assume then that the rate of change has been the same through time. Now that's a matter of sort of theoretical physics, and I think we'll have to deal with that at another time. But the first two, I think we can sort of think through. Like I said with the argon question, there are ways to sort of test whether these assumptions are valid.
Sure.
And I don't know if we want to get that much complicated. We're running out of time here. But there are ways. Let's just leave it at that. The assumptions that we make that go into, inferring a model age for a sample that we're given. There are ways of testing whether those assumptions are reasonable assumptions. Let's not say that, because you can never know absolutely for sure that you've got it right. It's perfect, and we have perfect knowledge, and we just know that this is absolute truth. But you can be more or less confident based on the kind of rock it is, how you've processed it, what you know about the radioactive decay, what you know about the chemistry of the elements involved, and so forth. You can say, I am confident that this date is reasonable, and I am not confident that these dates over here are reasonable. And so there you go. Now, with all of these assumptions that go into this, do you always get the same answer? If you took your scoria there and you had that dated and you maybe you broke it into three different pieces and you sent it to three different labs, would you get the same date from every lab?
Well, that's a very good question. And I think it would partly depend perhaps even on the particular radiometric method that you applied.
That's right. Yeah.
No doubt we'll come back to this in future episodes.
Yep.
But there is some intriguing data that suggests that actually different radiometric dating systems give systematically different dates on the same samples.
Consistent.
On the other hand, there is definitely a kind of broad trend that we see in the rock records. So if you take rocks that are known on the basis of other geological evidence to be relatively old, maybe they're down at the bottom of the geological column somewhere, those rocks will tend to give older ages than rocks which are up at the top of the geological column that are known on the basis of other evidence to be younger. And there is a broad trend. Now, there's an awful lot of scatter, and there are some anomalous dates, but nevertheless, there is a trend. Yeah. And one of the things that... one of the dangers I think that we need to avoid is to cherry pick bits of the data that kind of suit us, that suit the model we prefer. Yeah. What we need to do, I think, if we're to try and understand this in a truly scientific way, is to understand the trend, the broad pattern of the data.
That's right.
But also to understand the anomalies and the exceptions.
Yes.
And if we can come up with a model that enables us to do both of those things, then that is going to be a model that is preferable to a model which simply looks at the trend but ignores the anomalies.
That's right.
Or a model which focuses on the anomalies and ignores the trend.
Yes.
Right?
Yeah,
we want to try and explain the totality.
Yeah.
Yeah, the totality of the data.
Yeah. Yeah, I think you're right. And going back to your piece of scoria there, if we broke it into pieces and sent it off to different labs and told them to date it by the same method, you would think, theoretically, we would expect to get back dates that were broadly in agreement. I would not expect to get exactly the same date from each piece of the rock, because there's just random things that happen. And geological dating is like that, right? As you said, there's a lot of scatter, right? There's a lot, which basically in statistical terms means there's a lot of noise. There's a lot of stuff that's not quite hitting the same target. But I would expect them to be in the same ballpark, right? I would expect those dates to be, as you say, broadly consistent. And that's usually what people find. So when you hear about a new fossil and somebody says, this fossil is no younger than this, no younger than 1 million and no older than 2 million, that's some of the issues that happen with this geological dating, because you have all of these assumptions and all of these nuances and exceptions that have to go into this dating. And so you don't get a date that is, this was made on July 3rd, 30 million BC. It just doesn't work that way. It's messy.
No.
Real data is messy. Yeah.
Yeah, because we're dealing with real world systems, and real world systems have had a history. That's what we've been talking about. They've had a history.
Yeah.
And that history sometimes kind of messes things up. It's not quite as neat and straightforward as we would like it to be.
Right.
And I also think it's worth just at this point kind of emphasizing that sometimes a bit of subjectivity, goes into the interpretation of the data. Geologists are obviously wanting to try and test their assumptions and see how reasonable they are. But let's say that you've got a rock and you perform a radiometric dating test on the rock, and the date comes out broadly in agreement with kind of what you expected on the basis of other methods. Even if there was evidence that rock specimen had been an open system, and maybe there'd been some alteration, of the rock, some chemical alteration. If the date comes out broadly consistent with what you expected, you're probably going to accept that date is okay.
Yeah.
On the other hand, even if you had a very pristine rock sample, which you thought was not subjected to chemical alteration or, groundwater movements or whatever it is, but the date comes out completely inconsistent with what you were expecting on the basis of other results, you may well be very suspicious about that sample. You may think, well, there's something I've missed. Maybe there's something that has affected the rock but not left a signature. So there is a certain element of subjectivity as well that goes into the interpretation of dates, and you see that in the literature.
Yeah.
Now, this is not to say that geologists, I don't want anybody to think that we're saying geologists are
just guessing,
deceitful, or just guessing. It's all kind of just some big hoax. No, geologists are trying to do their best to understand the data that they're seeing in the real world, but nevertheless, these are complex issues, and we have to interpret what we're seeing. And so, that's really what we want to try and explore a bit in this series. Some of the complexities of this issue, but to bring it down to a level that most people can sort of understand.
Big job.
Yeah, big job. Now, that's probably a good place for us to break, I think, for this episode. And we will definitely come back to this subject again. Now, we don't know exactly what we're going to be doing in the next episode, so you'll have to come back in a fortnight to find out. But we'll have something equally fascinating sort of lined up for you. Just remember, all of our streaming platforms, show notes, all of the information about the podcast is available at coresci.org/podcast. That's coresci.org/podcast. That's kind of the homepage for the podcast. We love to receive your questions and comments. So if you want to send those, you can email us at podcast@coursesci.org. Don't forget to hit the subscribe button, hit the notification bell, like our episodes, share them on social media, tell your friends, encourage them to subscribe as well, leave us a positive review. All of that really helps us to kind of spread the word. And finally, as we always say at the end of these episodes, we are reliant on your support and your donations. So if you are enjoying the podcast, you enjoy the content that we're producing, please consider supporting us with a donation. If you want to support Biblical Creation Trust, you can visit our webpage at biblicalcreationtrust.org. There's a donate button. If you click that donate button, it will take you to a giving page, and all of the options are laid out there, including our PayPal account. Todd, how do people go about supporting Core Academy of Science?
Yeah, Core Academy is at coursesci.org/connect. There you will find links to all of our social media accounts, all of our blogs, all of our YouTube channels, and so forth. You will also find ways to support Core Academy at coursesci.org/donate. So check that out, please.
Well, that's great. That was great fun.
That was.
And and I'm looking forward to next time. So we'll see you in a fortnight's time.
Thanks for listening to this week's episode of Let's Talk Creation. If you have questions, send them to podcast@coursesci.org. That's podcast@coresci.org. And be sure to let your friends know about Let's Talk Creation. And check us out on social media. Thank you.